Welcome back, Science 8. Today we are going to talk about density, temperature, and buoyancy. Well, the chapter 3.3 talk about buoyancy, but this lesson video probably will cover mostly density and temperature. Last time we talked about what density is, which is how packed a material is in a given volume, and we talk about and did some example of density calculation. Today we are going to talk about relationship between these two specifically. Overall topic, instead of checklist, I can propose a question. I want you to think, do you guys think a density can change when the temperature changes? If you can answer this question after today's lesson, that means you learned a valuable lesson about the relationship between density and temperature. When it comes to relationship of two factor, like in this case, the question asks you density and temperature, we did something similar. It was about viscosity and temperature. When temperature goes up, flow rate goes up, when the temperature go up, we remember that the flow rate of a fluid went up, and we conclude that viscosity went down. So ultimately, we talk about relationship of those two. Similar like that, I want you to think about the relationship between these two variable, density and temperature, throughout today's lesson. In order to understand the relationship between density and temperature, we have to revisit what I like to call the particle model that we learned before. Particle model, we readily use it to explain the matter's physical state, like solid, liquid, gas, something like that. Plasma is not included. But in any case, each of the substance, one thing that we know is we have a certain amount of particle in a given volume. So we talk about that. That's a fancy way of saying we are not introducing this does not exist. We are not putting things extra because it's a given volume, or we are not let the matter escape also. Some people may wonder, what do you mean escape, Mr. Kim? Example can be evaporation. We are not letting those happen. So that means think about this environment as a closed environment. Then logically it makes sense. We should have a constant amount of quantity in a given volume if the temperature is kept constant. What I mean by that is, if I have 1, 2, 3, 4, where's my laser? 1, 2, 3, 4, 5 at the low temperature, that amount contained. As you can see, it's a sealed environment. So here's one thing that I want you to think about. And that's one of the conclusion already. Density, ladies and gentlemen, does not change. But it has a condition. As long as the temperature stays the same, which is a fancy way of saying if temperature is your controlled variable, then we do not need to think about, how can I say, the change of density. Temperature is the one that can affect. As long as it kept constant, there's no way the density will change. So most of the time, if you look up the densities, they have a condition like room temperature and room pressure is the one that they, when I say they, scientists, they use those conditions to calculate the density, like how we did last class, mass over volume. Room temperature, please write this down if you didn't know, it's 25 degrees Celsius, according to the scientific guideline. In real life, a little different. Let's go with an example and then we can get to our conclusion of the question. What's the relationship between the density and the temperature? So here's one thing. I want you to think about warm water and cold water. At this time, you guys should already be familiar of those relationships because last year, grade 7 science, you guys learned about heat energy. Warm water, cold water, in the end mix. So some of you guys also get to that conclusion that warm water floats and cold water technically sink. It's not written in here, so I'm gonna use a pen. However, you learn about the fact that when it comes to that environment, let's say this is warm water, cold water. In the end, you may notice that this will involve with the mixing if it was other way around. Or you may learn that if things are heated, like fire underneath, then you will get that cold water turning into warm water and warm water get cool and then goes to cold water. So there is a mixing occur. That's what you learn in Science 7. Now, when it comes to Science 8, I want you to draw the particle model that involved with that. So here's what happened. I want you to draw a beaker. Now, it's going to be very similar as the one on the right side. However, I want you to know that it is a little bit more complicated. I'm going to draw another beaker to get to that conclusion part, but the first one is important. So let's say we originally have water molecule H2O. What about we draw about, like 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, something like that. Please make sure that these guys are randomly colliding, like what we talk about, and we also have a source of heat. Now, source of heat is important because when it comes to temperature, let's think about which area you think will be more heated up. I can think about these two regions actually. The first region over here, I like to say this is relatively hot area. Some people say, why the bottom part is relatively hot, Mr. Kim? Well, we have a direct source of heat. So bottom part is relatively higher temperature. On the top part, can you see that it's more contacting the outside environment like air? That means this part is relatively cool. Now let's think about it then. If I have relatively hot situation at the bottom area, what would happen for the particles movement? The particles movement, and know the fact that this is a given volume, right? It didn't change anything. You will notice that the bottom part will move more crazy way. In fact, fast movement. On the other hand, the top part, they're gonna move relatively slower. Can you see I'm using one arrow and two arrow being a little bit more crazy ping pong ball you can think of. And when it comes to the top one, think about like a bowling ball. Bowling balls are slow. And I understand ping pong ball is way lighter compared to the bowling ball that is way heavier, but I want you to just think about the speed perspective. Then I want you to think about, you will notice that the bottom part, fast. They move fast. Top part, they move slow. Then probability-wise, what happened is this fast one try to escape, even though it's a closed environment, so they cannot technically escape freely. Then what's going to happen is, now this is where layers happening. But it's almost like invisible layer because water, well, it's the same kind, right? The fast ones are now trying to, actually, this one I gotta unbalance it just a little bit. If you think about probability wise, there will be faster one that will be located on the top because they are trying to escape this environment because it's too hot. I draw 4 of them in there on purpose because when it comes to, again, probability situation, the slow ones are the ones that tend to stay at the bottom or doesn't have enough of energy to travel top. As soon as that happened, now we have a little bit of conclusion. First of all, this is slower molecules. Top part, faster molecule. And if you notice how many are there, slower one cannot escape as much. So you may notice that we have more in there versus on the top, you don't have a lot. AKA, we went to the conclusion where warm water, why they stay on the top? Because of density, they have less number. On the other hand, when it comes to cold water or cool water, they're located at the bottom because the movement is slow. So we're getting into one of the conclusion. I use the water, warm water and cool water as an example. Same thing will happen for the air too. If you look at the particles movement, ladies and gentlemen, the particles in a substance move way more quickly when you have some kind of energy that is added. And the perfect example of added energy is, well, heat energy. If I have a heat energy underneath, then what happens is the motion of the particles will be way faster. This is like a double arrow that I draw in the previous one. Then a lot of particles try to escape that space. So you have relatively less particles in a given volume. On the other hand, when it comes to colder situation, we are taking energy away. That's what the colder temperature situation is. Anything that is cold outside, I know it's depressing, winter will come, negative 30 to 40. Hopefully it doesn't go that way, but it's common in Alberta. What happens is your body's energy is taken away, so you need to shiver. But in any case, cold air, you have more particles in a given volume. In a given volume, just because particles are slower. Therefore, as particles become more active, they move away from each other and the space between them increase. So what I mean by that is, like the picture suggests, I don't want to put a lot of emphasis on this one, because they're moving away a lot. Can you see the distance is further apart compared to the cold air situation? Same thing. Hot fluid, cold fluid. The only thing that doesn't change as much is solid situation because solid is originally packed. So the one technology that deals with this hot temperature and density control is the hot air balloon that you see on the right side. When it comes to density and temperature relationship, and I'm gonna put a little bit of conclusion in here. If the temperature is increased in the environment, particles move faster. That means there are lots of particles that move around like crazy. And what happens is this will cause volume that goes up. Some of you guys may notice how the volume is increasing. Well, think about it. Hot air balloon, the one that you see over here, this is a structure. It goes way beyond over there. Hot air balloon doesn't really have a volume to start with. It's just like tarp material that is connected at the centerpiece over there. But because we're applying the heat energy, which is combustible materials and combustion reaction that create the fire that you see at the middle part over here, that creates heat energy, particles moving more, particles actually hitting the surface more, so that's why volume goes up. If the volume goes up, density goes down. And I want you to ultimately know that temperature and density, one goes up, another goes down. We talk about this relationship. It's inverse relationship, just like viscosity. Now, I can even prove this mathematically. I want you to think about the density formula. Density is equal to mass over volume. Now, I want you to think about one part over here. Temperature, temperature increase, particles movement increase, and because of that, the volume increase. Do we have volume in this formula? Yes, we do. The volume is located at the bottom. So if I think about the volume, let's say volume goes up, then what will happen to the whole fraction value of it? It goes down. Some people who wonder, the denominator is increasing, so the whole fraction value is decreasing. I believe I mentioned this as an analogy, but I'll give you one more example. Let's say I have half versus, you know what, this time quarter. What about that? Half versus quarter. So let's say you have a student, Liam. Liam has a choice. Half of loaf of bread versus quarter of the bread. Which one he want to choose for his, I don't know, breakfast, lunch, whatever the meal. If I were Liam, I will choose 1/2 because half is actually more than the quarter. So in this example, like you see in here, I want you to know that if the variable is on the bottom of the fraction, it always affects the whole ratio in an opposite way. That's what we call inverse relationship. So ladies and gents, that was today's lesson. In next class, I'm going to have an exit slip. I think it's a 4th one, which is, like you guys know, exit quiz, if you will. It will be covering, or it will be about viscosity, density, and density calculation. Because it's a calculation related, you got that right, you need to bring your calculator. Most of the question you can do it using your mental math, but still, when it comes to density, there is a possibility of going for decimal, so please bring your calculator. Practice question. This is for homework, if you like to know as a homework. Textbook page 61, question 1 to 7. That is your to-do list. Just in case. See you guys next time.